All right, quiz warm up. Chain rule. Chain rule I have to use when I have a function on the outside and then I have a function on the inside. So my first idea here is that this 3 comes out front, and then whatever was on the inside is to the 1 less power. That's my first step in taking my derivative. This idea that's in here, 3x squared plus 7x minus 4, is unchanged. But then it's times the derivative of that which is inside. So we can call that 6x plus 7. Now, I think the hardest thing is getting used to what we do or do not have to simplify. I would not bother simplifying a single thing there. If you leave that answer on the quiz, you get it right. I don't have anything to cancel out. I don't have anything that's worth multiplying out. Because keep in mind why we're doing what we're doing. That is the equation of the slope of the tangent line. If somebody were to give me an xy ordered pair, because they want to know the slope of the tangent line at a specific point on the graph, then I can plug in my x and y, or I can plug in my x's and simplify. I do not have to add a dy dx because my y is already over here, nicely simplified. So that's y prime. So that lesson we learned on the last quiz, making sure that we understand that you have to let me know what it is you're finding, that y prime matters. Are we all good with that? Thumbs up if you got that right. You're on your way. All right. Next problem. My y prime is equal to the derivative of sine is cosine, but I got to be honest with you, I'm always going to take the time to write this like that. Do you know why? Does it make sense to you why I do that? So here's the thing, it's the sine is squared. Sine is a ratio of an angle. Sine is that unit ratio. Sine has a value. Sine of 4x has a value. That's what I want squared. I don't want 4x squared. We're not talking 16x squared. I want the sine squared. So lots of kids struggling with what this means. This whole value, the sine of 4x, that's one value. What is it? Here it is. Oh, square it. That's what this says. So this is a trig understanding that is super hard for kids because when this 2 is out front, that means I want twice that value. When this 2 is up here as an exponent, that means I want that value squared. And when this 2 is tucked in here with the x, that means that I want the sine of twice that angle. So if it was a 30-degree angle, twice that, 60. If I have a 15-degree angle here, I want 4 times that, 60 degrees. So whatever my angle measure is, we're going to multiply it by 4. We're going to get the sine of that, and then we're going to square it. So knowing where the coefficient is, super important. Okay. So if you're talking while I'm talking, 2 things are true. You're not listening to me, and you're distracting somebody else. So if there's something you want to talk about, I'll politely ask that you table it until we get through some of these and you have time to work. All right, so my outside function is going to be 2 times the inside sine of 4x to the 1 less power. There it is. Now it's time to take the derivative of what's inside. Here's my inside. I'm going to take the derivative of sine of x, which is going to be the cosine of 4x. By the way, I have to now take the derivative of what's inside. So that's going to be times 4. So for this one, I probably will, just to keep things neat, multiply my 8 times my 2 and have that be the sine, 8 times the sine of 4x times the cosine of 4 times an angle. Would you please, with your group, talk about these two? What do you want to remember? What do you want to make sure that you don't get tripped up on? Your market set talk. All right. Moving on. Now, none of that is implicit differentiation because you notice my y is already solved for. My y is on the outside. I don't need to worry about implicit. You do have to worry about the chain rule. You do have to worry about the product rule. You do have to worry about your trig. And if you flip your paper over, I can put any one of those things in. I can put E's and LNs and trigs and all kinds of whatevers. Okay? What makes an equation implicit is the idea that this y is not solved for. Now this one, I can solve for y. I can subtract x cubed, divide everything by 5, take the square root, and I can totally solve this one explicitly if I wanted to. I don't want to. Because now that we know implicit differentiation, I know I can call this 3x squared plus 10y to the 1 less power. And then I need to have dy dx here because the derivative of y in terms of x is equal to dy dx. I could add a dx dx after I take the derivative of x, but that goes to 1. Are we all okay with that? All right, so that's going to be equal to 10x to the 1 less power. And then, of course, the derivative of negative 12 is 0. So now my job is just to get this term by itself. So I'm going to unwrap it one layer at a time. So my first step is to subtract 3x squared from each side. So 10 times y dy dx is equal to 10x to the 4th minus 3x squared. I just moved that 3x squared to each side. You okay with that? Now I'm going to divide by 10y, divide by 10y, and I get dy dx, the change in y compared to the change in x, is equal to 10x to the 4th minus 3x squared over 10y. Done. I'm not going to bother simplifying anything. I know these 10s are friendly, but this 3 and 10 are not. There's nothing to do there, right? I know I could factor out an x squared, but why bother? It's not like I can cancel anything out, so I'm not going to. What I'm waiting for is if somebody gives me an XY ordered pair and says, hey, can you calculate the instantaneous rate of change at this point? Sure, I can plug in. But until somebody gives me an X and Y, that's good enough. We good on that? Okay. Next step. When I go to take the derivative of the next one, when I'm taking the derivative of the natural log, I'm going to just go ahead and put 1 over what it is I'm taking the natural log of. This is a chain rule, though, because here I have this inside here, this inside value. So the natural log of 5y is 5, say it with me, dy dx plus 6x is equal to negative 10. Now my job is to get this by itself, And I absolutely will simplify this because this 5 and this 5 cancel out so very nicely. And I'm going to go ahead and multiply or subtract by my 6x first. So I have 1 over y dy dx is equal to negative 10 minus 6x. So my algebra 1 days of having my x first, I kind of need to get over because I'm okay with that x wherever it is. Because like I said, I'm just waiting for an xy ordered pair for me to go ahead and give somebody what they need. If they need that instantaneous rate of change, they'll give me an input-output value and I can calculate it for them, no problem. All right, I'm going to go ahead and multiply each side by y. And I get dy dx is equal to y times negative 10 minus 6x. Make sure that's bubble wrapped. That y is multiplied by this entire quantity. If you want to, I just can't help it, my algebra 1 days are coming back, where I say it's negative 6xy minus 10y. With your group mates, would you please talk about what it is that you need to remember from these two examples on your market set talk? So when we start talking about higher order derivatives, I want to bring out to you, if you recall, here on Schoology, back in our derivative unit, not this more derivatives, but in the original derivative unit, I posted these two websites. The one was a website where you could play with and it showed you how we do the derivative. And this other one was this tracker website. And I want to show you some things about this just so you understand, just so you understand what it is that we're doing. Okay. So if you look here at this website, we have x squared graphed as my original function. And then here we see my tangent line, and we care about the slope of the tangent line. So if you look here, my slope is negative 2. That's what this point down here is. And as I slide my tangent line, that black line that you see being created is the graph of the equation of the derivative. So it's a quadratic original function. So of course the derivative is 1 power level less, which explains why my derivative is linear. The equation of my derivative line is linear. Thumbs up if that makes sense to you. All right, I've got a couple thumbs. Okay, reset. I can go into here and I'm going to change my function to a cubic function. And you'll notice that when I start to drag my derivative along my cube, you'll see I hit it where it zeroes out, and then I go back to it being positive. So I have a positive, zeroes out, and then it goes negative. So do you see how the graph of the equation of the slope of my tangent line, did you catch all those ofs? Is quadratic. So that makes sense that I go from cubic to quadratic. So what we're talking about today is the slope of this. Because we can keep on taking the derivative of the derivative of the derivative for as many powers as we have. And that's interesting because we can go back again to my quadratic and I can say, okay, there's my graph. I go from a quadratic function to an equation of my derivative that's going to be linear. What if I were to take the derivative of this linear? take it down 1 power of x. So go from x squared to x. From x to, what's one level of x below linear? X to the 0, which is, isn't that a constant? Yeah. So it's interesting as we continue to take the derivatives. So when we talk about why bother having these second derivatives, third derivatives, fourth derivatives, because I can continue to analyze the change of the change. So if you think about when you're sitting at a stoplight next to a car and the light goes green, if you floor it, you're both accelerating, but he's accelerating faster. So his rate of change is increasing at an increasing rate, and you're being a nice, good driver, following the speed limits and doing all the right things, right? My kids, the car we gave them to drive in high school was stick shift. So they would start off, but then when they had to shift and then keep going, that changed their rate of change. So we can start graphing that by looking at these higher order derivatives. So that's a little bit of the background of why we're doing what we're doing. And finding the higher order derivatives is really a lot of the same things that we've been doing and a few things that we need to make sure we remember. Okay, first of all, let's talk about the notation. So we've got a number of different ways of talking about our functions. In our explicit functions, and you might want to write the fact that these are in our explicit functions where y is solved for, our second derivative notation is just y double prime or f double prime of x. So if you see those two little tick marks, that means you're asking for the second derivative. You have to take the derivative of the derivative. So if you're a thinker, tell me what you would guess our third derivative notation is going to be. Yeah. So we have y to the 1, 2, 3 and f 1, 2, 3 of x. And we can continue going on and on and on for as many powers of x, because each time you take the derivative, it drops at one level. So if I started off with my function where my x was to my 8th power, I can take the derivative 8 times, because it's going to keep on dropping down, 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 down until I get to 0, which is that constant. And then, of course, the derivative of a constant is 0. So we can start looking at that. When we have an implicit function, and that's going to be what this guy is, when we have our implicit function and I'm taking my dy dx, that derivative is embedded, and it's going to be the derivative squared of y over the derivative of x squared. So it's kind of crazy that 2 pops into different, because I'm talking about that second level change in y compared to that second level change in x. So if you're a thinker, you can figure out where this one goes. So d3 of y over dx cubed. You okay with that? Yeah? Okay. All right. So when we find my second and third derivative, now just because we know how to do implicit functions doesn't mean they're always going to be implicit. So when we go ahead, we can just go ahead and say here that my first derivative is going to be equal, and this is just my power rule. So 6x to the 5th minus 8x to the 3rd plus 10x minus 3. Not a problem. So then when I go to take my second derivative, I'm just going to take the derivative of my derivative. And you wonder, how many times can we say the derivative in one lesson? And you'll notice that each time my powers of x go down 1, and I drop a term because the derivative of a constant is 0. So that's my second and third derivative. But if you want to have just a jammin' good time, go ahead and find the fourth derivative. And you can then find the fifth derivative. And you can keep going. That's the fun. Calculus is the fun that keeps giving. With your group mates, tackle the second and third derivative of our next function. Go, talk about it. Go. All right, do we agree?
Yes, the first one.
Yeah? So it's interesting when you see, if we start off with an x, it's interesting because if we have an x power, it goes down to the 0, right? We lose the x and then it goes to a constant, a derivative of a constant 0. But if we start off with an x to the negative exponent, like, look, we can go on forever, right? That x is just going to keep on going power-wise. And that's an interesting conversation about that. Okay, so not so bad until we get here. So here we have finding the second derivative for our lovely sine function, and it's an implicit function because, as you notice, y, and there's no way of solving for y because it's the sine of y, and then x plus y. So our only way to tackle this one is through implicit differentiation. So it's not too bad. Here we go. I will warn you. Would you go ahead and draw a little squiggly line because you're going to need this half in a minute. I'm not kidding. But we'll start over here. All right, ready? When I go to take sine of y is equal to x plus y, the derivative of the sine of y is, of course, cosine of y. And I don't need to do anything except for remember to take the derivative of what's inside, right? What is the derivative of y? There it is. Oops. And that's going to be equal to the derivative of x is 1. And the derivative of y is, oops, where did it go? Oops. Gosh darn it. I was trying to make it green. Are you okay with that? All right, I need to get my dy dx's on the same side. So I'm going to say the cosine of y times dy dx minus dy dx is equal to 1. And then, of course, I'm going to factor dy dx out. And I have the cosine of y minus 1. And then, of course, I'm going to solve for dy dx by saying that's 1 over the cosine of y minus 1. Not too bad. Are we okay with that? Okay. So now we're going to find the second derivative of this same function. So this same function, I think I can paste it. So if I wanted to find my second derivative, my d2y over dx2, when I go to take this, I can either do the quotient rule, or I can just rewrite this as the cosine of y minus 1 to the negative first power. If you prefer blue, rock on. If you prefer purple, that's where I'm going to go. So when I go to take the derivative of this function, that negative 1 comes out front, times what's inside, to the 1 less power, chain rule, times the derivative of what's inside. What is the derivative of the cosine of y? Negative sine of y. What's the derivative of y? Do I have to worry about the derivative of 1? Why not? Because it's a constant. Be okay with that? So far you're like, no big deal. Right? So we're going to go ahead and say that d2y, we're going to clean this up a little bit, dx2 is equal to this negative of this 1 and this negative on that sine of y end up canceling out. So that sine of y, and we'll go ahead and put this cosine of y minus 1 squared back down in the denominator when he goes. And what the heck do I do with this dy dx? You're like, leave him be. If only I knew what dy dx was equal to. I sure do wish I knew what dy dx was equal to. If only, it's like Dorothy and the Ruby Slippers. If only I had a way to go home this whole time. You do know that movie, right?
Yes.
I'm genuinely afraid for the day that I make a reference to the Wizard of Oz and kids are like, d2y over dx squared is equal to the sine of y over, why are you talking and not riveted by this amazing revelation? Isn't that cool? So this can be substituted in for what we wished we had. We're like, I wish I knew what dy dx was. Well, look at that. There it is. And it happens to be something that I can simplify. How very cool is that? So, just the same as you're all going to ask, is this on the test? Yeah. And if you get this far, you'll get some of the points, but not all of the points. Because you need to know to plug this in for that. Okay? Okay. Yes.
If we write the next line down, like, that you had, and we just, like, the second to last line, if we
This one? Yeah.
will we get the point still?
I probably will still give you the point, but how could you resist simplifying? Oh, good luck. Everybody say hi to Miss McDonald. Anybody remember Miss McDonald from her middle school? Miss McDonald. Do you recognize? Did anybody have Miss McDonald? Look at all your friends. Have a good time. Enjoy. Text me. Okay. Ready? Look, look, look. Here's more. Let's have a good time. Ready? Sure, why? Haley. Right?
You cancel the 5-7?
Yes. Right? Here we go. Good times. So how nice was this? No chain rule, no embedded anything. Not implicit. Just do your thing twice, right? So this is why, like, somebody who struggled last unit in Unit 3, we're reviewing every day. More practice, more practice, more practice. It's so good for us. Why can't I write that as negative sine x over x squared? Because it's not multiplication, right? It's minus. Catherine says, I agree. The only thing that you could maybe do is if you wanted to factor out a -1 and make it positive sine of x plus. Why not? Right. It doesn't seem like it would be worth our. All right, ready? Y is equal to cosine of x. We'll go ahead and say that y prime is equal to. Now remember, if you need to rewrite this as that, please do, so that you see your chain rule. So that's 2 times what's inside to the 1 less power times the derivative of what's inside, which is negative sine of x. Oh, do you see what we're going to do next? Do you see it? Here it comes. it in the right order. Do you guys like to do the derivative of that first term first or write the first term? Write the first term. 2 times the cosine of x times the derivative of the second term, which is going to be the opposite of cosine. Plus, yeah, because it is negative sign. That's a product rule. And then my first is the opposite of the sine of x. Oh, you guys do a different order. Hold on. I'll make it nice for you. Because you want to do the derivative of the first, right? We haven't done that yet. So the derivative of the cosine is sine, so this becomes, I'm going to do this as minus. Times my second term, which is the opposite of the sine of x. So y double prime is equal to, we'll pull that negative out here, negative 2 cosine squared of x, and these two negatives cancel out, plus 2 times the sine squared of x.
Why is it minus 2 sin x?
Because when I took the derivative of cosine, it's minus sine.
Oh, it's negative sign.
Yeah. Ready?
No.
3 derivatives. This one's easy. This one's easy because there's no parentheses. Basically, you're like, woohoo, no parentheses. There's no e's, no logs, no trig, no negative exponents, no radicals. This is a beautiful, fun. And Marcus said, go have fun.
I know my times table from I know like 1 to 12. But like each one I know.
No, it's like embarrassing. If you didn't get in that
Now it'll
No, you'll get in.
My bad, guys. Give me a second.
Yeah.
You're all.
How we do it?
Mr. Glacier, can you just go back up?
You said write it out.
I'm crazy. All right, so these last two, Jacques and I just stayed after to do. And we've both figured out where we mess up. I keep forgetting to take the derivative of y. And then when it comes time to plug in what we know dy dx is equal to, that's where this in red comes. And then we can simplify because we were given an xy ordered pair. And this is where we substituted in for x and for y. If you give me an exact answer or an estimated one, they're both okay. And then for the next one, my derivative is this. So my second derivative is going to look like this. Don't forget to take the derivative of y. And then when you go to substitute, this has to go in here. All right?